Hello everyone, welcome to Practically. We bring learning alive. Fine then. So we are discussing sample papers and already as a part of it, class 12 biology completed as well as chemistry also completed, and today we are going to discuss a sample paper from the physics subject, which is according to the CBSE term 2. Okay, so already you are aware of the board, the sample paper which is released from the board regarding term 2. So if you see that, in that we are having 3 different sections named as section A, B and C. Section A, it consists of 2 marks question, 2 marks questions. That means 3 2s are 6 marks. So section A carries 6 marks. Next, section B, 8 questions will be there with internal choice. Again, 8 3s are 24. So each question carries 3 marks there. 24 plus 6, we are having 30 marks. And then section C. Section C is case based questions. Okay, so that case based questions related to the case study, based on a paragraph will be given, and based on the paragraph will be asked some questions and you have to answer it, and that will be for 5 marks. So 30 plus 5, 35 marks overall. And then okay, few of our friends watching, am I audible? Whoever are watching, just respond whether I am audible or not. Yeah, students, just let me know, am I audible or not? Say yes if I am audible. I mean, just type there, I can see. No? Am I audible? Just please respond, whoever are watching. Okay, fine, I hope so. Fine then. So it's for 35 marks. How the questions are segregated, just now I said. It's of 2 marks, 3 marks, as well as 1 case study, 5 marks. 2 mark questions, 3 will be there, 3 2s are 6. 3 marks question, 8 will be there, 8 3s are 24. And the case study, 1 case study will be given, that will be for 5 marks, and overall 35 marks. And then coming to this internal choice, there is no overall choice, but there will be an internal choice. However, you have to attempt all the questions mandatory. Okay, so all the 12 questions whichever will be given, that you have to give an attempt. Okay, fine then. I am going to start with the first question. Yeah, here is the first question. You can see the question number 1 here. Draw a neat ray diagram of a simple microscope. Write the formula for its angular magnification when the image is formed at the least distance of distinct vision. So least distance of distinct vision is nothing but it's the minimum distance at which objects can be seen clearly without any strain by the human eye. That's what least distance of distinct vision in general. So here they are talking about simple microscope. So simple microscope, a convex lens which is having a short focal length will act as a simple microscope. So draw a neat ray diagram of a simple microscope. So how we are going to draw? Let us see. As I said, this is the convex lens. That too, convex lens will act as a magnifying glass. That's nothing but simple microscope. When an object is placed between in its focus as well as optic center. So I am taking the optic center over here, and let this is the focus of the convex lens. If I keep the object A, B, let it over here, then so this is the line which is parallel to principal axis. So as I mean 2 minimum number of light rays are required to represent this ray diagram. 1 light ray I will take parallel to the principal axis. So then refracted light ray, okay, will propagate through the focus. So this one, another one I will take through this optic center. So they won't intersect over here, they won't meet over here. If I extend both the light rays, so they may be meet at this position. Let this is the image of the object, let it be. So AB is the object, A dash B dash is the image of the object. Alright, so here we have to obtain the formula for its angular magnification. What is meant by angular magnification? Angular magnification is defined as the ratio between angles to the angle subtended by the image to the angle subtended to the object with respect to the eye, or in terms of least distance of distinct vision also you can say. Magnification, angular magnification of the simple microscope can be defined as the ratio between angle subtended by the image at the least distance of distinct vision divided by angle subtended by the object at the least distance of distinct vision. Okay, so like that also you can define. Now anyhow we have to derive an expression for it. For that I am taking here and simple adjustments here. The AB parallel to this I am marking here for convenience, let it be A double dash. Okay, so angle subtended, so this is the eye view, from here we are observing this. Okay, angle subtended by this image with respect to this eye, I am taking it as beta. Okay, and angle subtended by the object, suppose if this is the line that I am taking here, let this is alpha. So this is alpha. Object distance with respect to the optic center, let it be x. Image distance with respect to the optic center, let it be d, which is nothing but least distance of distinct vision. Okay, so angular magnification can be defined as, just now I said, angular magnification can be defined as the ratio between angle subtended by the image at least distance of distinct vision by angle subtended by the object to the least distance of distinct vision. That means beta to alpha. Here I have shown it as beta and alpha respectively. So we can make it as beta and alpha. What does beta here? Beta and alpha here, there are small angles. So for small angles I can take an approximation here, tan beta as well as tan alpha. So if you look at these triangles once again, there are two triangles which you can see here. One is triangle OAB. Okay, that's looking like this. Okay, which is x. So here that will be beta. And another triangle you can see, this I am taking, which is with respect to the distance, least distance of distinct vision, that is D here, O, A dash, A double dash. Okay, so and this is alpha. Now as I said here, angular magnification, let it be M is equals to tan beta by tan alpha. Tan beta is equals to, you can write opposite by adjacent. So opposite side here AB by adjacent side OA divided by tan alpha is, again it is in terms of tan, opposite side A dash, A double dash divided by OA dash. Alright, so here AB by, AB as well as AA double dash, both are same from the diagram. So then I will cancel these two will be cancelled out, then we will get here OA dash by OA. From the diagram, OA dash means D, capital D, least distance of distinct vision, by OA means x. So then it will be D by x. So M is equals to D by x. Keep it aside. We have to calculate the M value for the least distance of distinct vision. Now we will use the simple convex lens formula. What is the lens formula? By using lens formula, so in examination you have to write the each and every step very clearly. Alright, and this arrow marks, everything you have to mention. If you are not mentioning, again it may lead to the reduction of marks. Okay, fine. So here by using simple lens formula, 1 by f is equals to 1 by v minus 1 by u. 1 by f, focal length, we have to find the magnification in terms of its focal length. So then 1 by f I am keeping like this. 1 by v, v is image distance and this is object, this is image. So image distance is d, which is left hand side to the optic center. By using this new Cartesian sign convention, the sign convention here for the least distance, I mean image distance, will become minus d here, negative. Minus 1 by u represents object distance, which we are aware of. So here OA is object distance, which is nothing but x, that is also left side to this optic center. By using new Cartesian sign convention, we can say that is also minus x. Alright, so this minus 1 by d I bring to this side. 1 by f plus 1 by d is equals to minus of minus, it will become 1 by x. And here m is equals to d by x. From here 1 by x is equals to, we can write it as m by d. So in the place of 1 by x, now we can substitute m by d. That means 1 by f plus 1 by d is equals to m by d. Okay, if you bring d to this side, then m you can write it as, this is also d, don't confuse again. It will become d by f plus 1. Therefore, magnification, angular magnification of the simple microscope will become m is equals to 1 plus d by f. Yeah, Ashok. Hi Ashok. Fine. How are you? Can you hear me? Okay. So this is how we can obtain the expression for angular magnification of a simple microscope for the distance, for the image at the least distance of distinct vision. And here one more case also there. That is what? Finding the magnification when the object is at infinity. That case also there, but anyhow in this question you are given, find out this magnification, angular magnification of this simple microscope when the image is formed at the least distance of distinct vision. When it is formed at infinity, that is another case. Okay, so now in this case m is equals to 1 plus d by f is the answer. This is how it will be. So very simple, it's a very simple application of ray diagram. That to what? Image formation by the convex lens. When object is placed in between the focus and center of curvature, focus and optic center of the convex lens, then it will act as a simple microscope, which we are calling it as magnifying glass. Alright, so this is how we have to derive it. Right, let's move on to the next question then. Explain the laws of photoelectric emission on the basis of Einstein's photoelectric equation. Einstein's photoelectric equation, very very important. There are some postulates about it. So just listen here. Photoelectric emission on the basis of Einstein's photoelectric equation. Einstein's photoelectric emission, photoelectric effect is explained based on the Planck's quantum theory. According to Planck's quantum theory, this light will be propagated in the form of small discrete photons, discrete packets, which we are calling them as photons. With each photon will be having an energy E is equals to h nu. Okay, this we are aware of already. All right, actually this his analysis, it's the Einstein's photoelectric equation. This theory he explained based on the interaction of the two particles. What are the two particles? One is photon of the incident radiation, Second one is the electron of the photosensitive cell, photosensitive metal plate. Okay, so what is that? He has explained this theory based on the interaction of the two particles. One is photon of what? Photon of incident radiation. Second one is electron of photosensitive metal plate. So this is a theory question. I will explain based on this content. Okay, fine. Photon of incident radiation and electron of the photosensitive metal plate. And next, when this actually these electrons, whichever I said, that free electrons, they will be bounded to that photosensitive metal plate due to certain restraint forces. Okay, due to the restraint forces, those electrons will be bounded to the surface of the photosensitive metal plate. Okay, when that light incident on the metal plate, that means it's just nothing but energizing. All right, so when that photons incident on the metal plate, then the energy of the photon will be utilized in some ways. So what are the ways? Some part of the energy of the photon, is utilized to liberate the free electron. I said free electron is presented, right? It's bounded to the surface of the photosensitive metal plate. So part of that energy is used to liberate the electron which is there in the metal plate, and some another part of the photon, I mean that energy will be utilized, will be imparted as kinetic energy to the electron. That means we will call them as photoelectrons. Suppose if this is the metal plate where free electrons are there, so whatever the incident radiation, if I say that E is equals to h in nu is the amount of energy, then this part of this energy will be utilized to liberate the electron. How much work is required, how much energy is required, that we will call it as work function, which is represented with W naught. Okay, so partly it is utilized to liberate the electron, that to liberate it this much work should be done, that work done we are calling it as work function, and some other part of this energy will be imparted as kinetic energy to that photoelectron, which you can write it as half mv square, let v is the maximum. So in such case we can write here that half mv square is equals to, we can write it as h in u minus that work function. Okay, so here mostly the less than 1% of the photons only can impart the energy to the photoelectrons. So maximum of the photons, they will spend their energy to liberate the electrons from the photosensitive plate. That's what most of the energy will be utilized, most of the photons will utilize their energy just to liberate the electrons, nothing but which is equals to the work function. So if I say nu naught is the threshold frequency of such a photon, that then amount of energy that is utilized by it will become, let it be, E is equals to h in nu naught. Okay, this amount of energy will be utilized only to make electrons free. Okay, so then this kinetic energy will become h in nu minus h in nu naught, that is h common if you take, it will be nu minus nu naught. So these equations, these two equations, we'll call them as Einstein's photoelectric equations. These are called Einstein's photoelectric equations. Now actually this is the theory that I have explained to know very clearly about the laws of photoelectric emission of the Einstein's photoelectric equation. So first you should know what exactly the Einstein's photoelectric equations are, then only you can go for the laws. Now let us see answering this question. So what are the laws? I have given the description for this Einstein's photoelectric equation. First one, effect of intensity of the radiation. So intensity of the radiation is nothing but it's the number of photons incident on the photosensitive plate per unit time. Okay, so as I said, whatever the photons that are incidenting, they will use the energy to do something, what it is utilizing to liberate the electron and to impart the kinetic energy to the photoelectrons. So that photoelectron rate, emission of the photoelectron rate will depend on the incident radiation. That's the first one. As I said, the question is what? Laws of photoelectric emission, right? So effect of effect of incident radiation. I'll write here. So let me arrange these points. Yeah. So first one, okay, first one, effect of incident radiation. Okay, so this says that the emission of the photoelectron rate will depends on the amount of incident light ray, that incident energy. Okay, second one. So what if the threshold, the frequency of the incident photon is less than the threshold frequency? What will happen? Say we have got the equation as kinetic energy is equals to h into nu minus nu naught. Suppose if nu less than nu naught, this kinetic energy will become negative. Physically, there is no meaning for the statement. There is no meaning for the statement when if I take this condition. That means the frequency of the photon, whichever is going to incident on the photo sensitive plate, if it is less than the threshold frequency, then there won't be any kind of photoelectric emission. It's not possible. There is no physical meaning of it. Okay. Next, what if nu greater than nu naught? Same thing. Actually, this I said Ke is equals to half m V max square if it is the maximum one, which is proportional to the frequency here, let it be. Okay. Suppose the more and more incident light ray is what is amount of energy incidenting on the surface, number of photons that are going to incident per unit time, that rate will increase. So then kinetic energy also increase. But it doesn't mean that it is depending on the intensity of the radiation. So even if nu greater than nu2, the kinetic energy of the photoelectrons is independent on the, it is completely independent on the intensity of the radiation. That's the another important point. Next one, about time lag. What is this time lag? Yeah, so when this photon incident on the photosensitive plate, part of its energy is utilized to liberate the electron, and some other part will be as what I can say, imparting the kinetic energy to that photoelectrons, right? So in this here, that electron will take the energy from the photon. It will take it from the photon. That taking process will be done in a lump sum. That means in that single instant it will be happen. It's not like some discrete continuous process of energy. So that photon will deliver it, electron will take it. So both that delivering and the taking here will be happen at the same time, quick time. There won't be any kind of time lag. So that's what, no time lag here. So these are the laws of photoelectric emission on the basis of Einstein's photoelectric equation. All right. So that's what about this question, and this question is having an internal choice, and the choice question, if you see here, this is based on atoms, and this is and this we have seen here. And now let's see this next question. Okay, I am erasing that. Yeah, so internal question, if you see, internal choice question, if you see, figure shows energy level diagram of hydrogen atom. Yes, so these are the energy level diagram of hydrogen atom. Find out the transition which results in the emission of a photon of wavelength 496 nanometer. Okay, which transition corresponds to the emission of the radiation of maximum wavelength? Justify your answer. Okay, so see here, simple, it's very simple one. Energy transition mechanism we will use to solve this question. So what is that? So now here hydrogen, that energy level for with respect to this photon wavelength, I am calculating first. E is equals to h nu. We know that nu is nothing but we can write in terms of cy lambda, in terms of speed of light as well as wavelength of it. So 6.63 h value into 10 power minus 34, c value, speed of light, it is 3 into 10 power 8. As we are expressing this energy in terms of electron volt, So this lambda wavelength here, it is 496 nanometer. That is nothing but 496 multiplied by 10 power minus 9 actually. All right, multiplied by 1.6 into 10 power minus 19. Why? We are representing this energy in terms of electron volt. If you simplify this, we'll get around 2.5 electron volt. All right, so now the question is, find out the transition which results in the emission of the photon of the wavelength. So we have to calculate the energy transitions here, like what? 4 to 3, 4 to 2, 4 to 1, similarly 3 to 2, 3 to 1 and 2 to 1. After calculating those energy levels, one energy level will map with this one. So that transition will be the answer. So for that, we should know the values. The E1 energy level, first level of the hydrogen atom here, that energy level diagram, how much it will be? Minus 13.6 electron volt. And to calculate the remaining, we are having that En is equals to E1 by n square formula. So by using that, you can calculate E2 value, it will be around some minus 3.8 electron volts. Okay, and E3 will be around some minus 1.8 or 1.51 electron volt, and E4 will be minus 0.85 electron volt. So this and all, you don't worry, you can calculate by using this formula. Okay, now you have to calculate E4 to E3 transition, E4 to E2 transition, E4 to E1 transition, then E3 to E2 transition, then E3 to E1 transition, then E2 to E1 transition. So after finding this E4 minus E3, E4 minus E2, E4 minus E1, we will get the values. So in this question, after simplifying that, the energy transition of E4 to E2 will become 2.55 electron volt. So sorry, excuse me. So in this question, in this particular question, the emission of photon of wavelength 496 nanometer will become for the transition of E4 to E2. Okay, and if you calculate this one, you will be having some 0.66 electron volts in this case, and which will be the least of these overall, whatever you are going to get here, whichever will be the least here. I mean, among all these energy transitions, this will become the least one. So the next question, which transition corresponds to the emission of radiation of maximum wavelength? If you look at this formula, how this energy and wavelength are related here? Inversely proportional. That means the more the energy transition, the minimum the wavelength. The minimum the energy level over there, the maximum the wavelength. So I said among all these things, you will be having the least for this transition. So which transition corresponds to the emission of radiation of maximum wavelength? That will be what I say, 4 to 3 transition. This will be 4 to 2 transition. Why? This is the explanation. Since energy over here, it is reciprocal to the wavelength. Okay. That is how you have to answer this question. Okay, hope I am clear, and let's move on to the next question. Assuming that the two diodes D1 and D2 used in the electric circuit shown in the figure are ideal, find out the value of the current flowing through 2.5 ohm resistor. Okay, so here you are given a diagram. Hope it's visible to each and every one. Yeah, I'll redraw it. That consists of the diodes like this. There is a resistor in series with it, and there is another diode over here, and one more resistor in series to it, and this is voltage supply with a resistor over here. Now supply voltage is 10 volt and 2.5 ohm is this value, and this is 3 ohm, and this is also 3 ohm. This is D1, this is D2. Now we have to find out current. So see here, this is a PN junction diode setup. A PN junction diode can conduct only in forward bias, which we already know that, and it won't conduct in the reverse biasing case. So first we should know which is forward biased and which is reverse biased here. So this is P side and this is N side. This is P side and this is N side. Okay, so P side is connected here to the positive terminal of the source, and whereas here end side is connected to the positive terminal of the source. So that means this is reverse biased, this is forward biased. So the one which is in forward bias only will conduct here. So D1 won't conduct here, only D2 will conduct. That means this you have to take it as open circuit. This is open circuit. So now 3 and 2.5, this and this will be in series. Alright, since this is, though it is existed, but according to the concept it won't conduct since it is in reverse bias case. This part alone will conduct then. That means diode D2 will conduct here because it is in forward bias. So then resistance we will calculate. Total resistance is equals to this and this are in series. 3 plus 2.5 will be giving 5.5 ohm. As our requirement is to find out the current here. So current I is equals to voltage by resistance. Source voltage is given as 10 and 10 by 5.5, which results from 1.8 ampere. Okay. All right. So this is how you have to calculate from semiconductor electronics. This is. All right. Let's move to the next question. Hope I am clear. Yeah. Here is the one. Theory 1. Let us see here. Electromagnetic radiations with wavelength lambda 1 are used to treat muscular strain. Having wavelength lambda 2 are used by a FM radio station for broadcasting. Lambda 3 absorbed by the ozone layer of the atmosphere. Okay. So now what are that radiations? That naming we have to give. This is the from electromagnetic waves. Here it is, see, it's very clear. To treat muscular strain, IR radiations will be helpful. So infrared radiations. First one answer is infrared radiations. Infrared radiations are used to treat muscular strain. Next, very high frequency VHF radiations. VHF radiation we will use in a FM radio station for broadcasting purpose. So this is VHF, very high frequency radiation. And lambda 3 are absorbed by the ozone layer of the atmosphere, which are that ultraviolet radiation, UV radiation. So in this question, lambda 1 radiations are corresponding to infrared radiation, lambda 2 is corresponding to that VHF radiation, lambda 3 is corresponding to UV radiation. Okay, that's the one. And in fact now we entered into the 3 marks question, so one carries 1 mark, one each 1 mark, so 3 ones are 3. All right, let's move on to the next question then. Yeah, fifth one. Derive an expression for the refractive index of a prism in terms of angle of prism and angle of minimum deviation. So we have to derive an expression for the refractive index of a prism in terms of angle of prism as well as minimum angle of deviation. Okay, fine. See, let us take a prism. First I will show that how refraction of light is happening in a prism. Here this is a rarer medium and this is denser medium. When light incident on the one of the refracting surface of the prism, see, this prism consists of 2 refracting surfaces which are at an inclined at an angle, subtend at an angle of prism, which we are calling it as. All right. So now here this is the normal drawn to this surface. Let angle of incidence over here, let it be I am taking. As this light is traveling from rarer to denser, it will bend towards the normal. So this will be the first refraction of light, and again this will touch this another side of the refracting surface at this position. So here as it is traveling from denser to rarer, it will move away from the normal like this. All right. Now here this is the actual path of light, and this is what the refracted path. So here angle through which the light ray has deviated is what angle of deviation, let it be delta. This is angle of prism, let it be A. So for convenience I'll extend this and it will become like this. Now you can mark this as P, Q, R, and this as M, N, S. So here this MNSP, this one, it's looking like a from this it's like rhombus shape. From this you can say let this angle is some theta I am taking. Okay, so I can say from this PMNS quadrilateral, okay, it's a quadrilateral where this sum of these two angles will become 180 degree. So I will write here A plus theta is equals to 180 degree. Okay, and now on other hand, if you look at the same diagram, here you can find out which one, yeah, you can take this one. So here I mentioned this as angle of incidence, let this is angle of refraction, and this is angle of incidence over here R dash, and this is let it be I dash. Okay, angle of emergence through which that is emerged out from the surface from this prism. So here R, R dash and N, which makes this is S, M, N, it's like a triangle. Sum of these angles in the triangle will be what, 180 degree. So R plus R dash is equals to, sorry, plus theta is equals to 180 degree. If I see this equation A plus theta, A plus, in the place of theta we can write it here as 180 minus R plus R dash, which is equals to 180 degree. Just I substituted here, then it has become what, A plus in the place of theta 180 minus of this whole. Okay, so it will become A is equals to R plus R dash, remember this. Okay, on other hand you can see this is R, so this will become I minus R, this will become I dash minus R dash. So these two are the interior angles and this is an exterior angle. Exterior angles is, sum of the interior angle is equals to an exterior angle. That means delta you can write it as I plus R plus I dash, sorry. So this is I minus R, right? So I minus R plus I dash minus R dash. Simple. I applied here exterior angle is equals to sum of the interior angles. So then we got here delta is equals to I plus I dash minus R plus R dash. But R plus R dash means it is A. So delta is equals to I plus I dash minus A. If you bring A to this side, then A plus delta is equals to I plus I dash. These are the two relations which we have obtained. Our requirement is derive an expression for the refractive index of a prism in terms of angle of prism and the angle of minimum deviation. So under that minimum deviation condition, through angle of deviation is nothing but what, angle through which the incident light ray will deviate from its path. So then we are calculating that for minimum angle of deviation. If delta is the angle of deviation, let's say delta m is the minimum angle of deviation. Under that condition, this light ray will be parallel to the refracted light ray will be parallel to the surface. There we can write it as I is equals to I dash and R is equals to R dash. Okay, from this diagram here, then it will become here A will become A is equals to, as I said, R plus R dash, it will become 2R. That means R is equals to A by 2. Okay, similarly delta will become here A plus delta minimum. I am writing here since delta is delta minimum here. So here delta minimum nothing but minimum angle of deviation. A plus delta minimum is equals to I plus I dash. That means I plus I, that is equals to 2I. So I is equals to A plus delta minimum by 2. Now from Snell's law, From Snell's law, we know that sin I by sin R is equals to mu. Sin I by sin R is equals to mu. So that implies refractive index is equals to mu is equals to sin of I means what? A plus delta minimum by 2 divided by sin A by 2. That is the expression for the refractive index of the prism in terms of angle of prism as well as minimum angle deviation. Okay. Yeah, Shabana. Hi. How are you, Shabana? Can you hear me? Okay, fine. So this is from this we can obtain from the Snell's law. Derive an expression for the refractive index of a prism in terms of angle of prism and the angle of minimum deviation. This is how we can obtain. Sin I by sin R is equals to mu, then mu is equals to sin of A plus delta minimum by 2 divided by sin A by 2. So to achieve that, you should know these expressions, and then as we are talking about minimum angle of deviation, under that certain conditions will be there. We will apply that condition and henceforth we will get the final one as mu is equals to sin of A plus delta minimum by 2 divided by sin A by 2. Okay. So when you are given this derivation neatly by explaining step by step, you should derive it. Alright. So that's all then. Let's move on to the next question then. Yeah, see here. Yeah, question number 6. Okay. 6a. Two coherent sources have intensities in the ratio 25:16. Find the ratio of the intensities of maximum to minima after interference of light colors. Okay. And then question B. Yeah, question B. In Young's experiment, the width of the fringes obtained with light of wavelength 6000 angstrom is 2 mm. Calculate the fringe width if the entire apparatus is immersed in a liquid medium of refractive index 1.33. Okay, fine. See here. Here generally we know that intensity is depending on the amplitude, square of the amplitude. So intensity's ratio is given, that is I1 is to I2, that is 25:16. So here I1 is equals to A1 square I will take, which is as 25, that means A1 will become 5. Similarly I2 is equals to A2 square, which is 16, then A2 will become 4. Then find the ratio of intensity of maxima to minima. Intensity of maxima to minima, that means I maxima to I minima is equals to, formula here in terms of amplitude we can say A1 plus A2 whole square divided by A1 minus A2 whole square. That means here A1 is 5, A2 is 4, 5 plus 4. 5 plus 4 by 5 minus 4 whole square. 9 square by 1. That means 81 by 1. So 81:1 is the answer. Okay, that's how you can solve this question. And now next question B here itself. Young's experiment, width of the fringes obtained by the light of wavelength 6000 angstroms is 2 mm. Okay, so generally the fringe width in air beta is equals to, we can express it as d by small d into lambda. But when this apparatus is immersed in the liquid, then how that fringe width will be, nu1 will become beta dash is equals to this d and small d, that distance that will remain same, and lambda will become, let it be lambda dash, d by d lambda dash in terms of the original wavelength and refractive index, you can write it as lambda by mu. But d lambda by d nothing but beta, so we can write it as beta by mu. Beta value is given as 2 and mu value is 1.33. This is mu and this is beta here. So 2 by 1.33 will become 1.5 millimeter. Okay, so that is how you can solve this question. This is another 3 marks question, right? Okay, yeah, Christo, hi. See the next question, question 7. Show that the superposition of the waves originating from the two coherent sources S1 and S2 having displacement y1 as a cos omega t and y2 as a cos omega t plus phi at a point produce a resultant intensity I is equals to 4a square cos square phi by 2. We have to show it. Hence write the conditions for the appearance of dark and bright fringes, that means maxima and minima. Okay. Constructive interference and destructive interference. Okay, fine. So here I think it's not visible over there on the screen. So this is nothing but we have to prove it as I is equals to 4a square cos square phi by 2. Okay, let's see here first. So then they said on superposition. So when those two are superimposed, then the resultant will become y is equals to, we can write it as y1 plus y2. All right. So then y1 is what here? A cos omega t plus y2 is what here? A cos omega t plus phi. Then here a you can take common, it will become cos omega t plus cos omega t plus phi here. Cos x cos y, cos x plus cos y, cos of x, 2 cos x plus y by 2, cos x minus y by 2. That formula I am applying. Cos a plus b, or you can take cos a plus cos b. Cos a plus cos b, 2 cos a plus b by 2 into cos a minus b by 2. Then here if I apply it, as 2 is there, I am writing 2 here. 2a cos x plus y by 2. This is x and this is y. If I say x plus y by 2, omega t plus phi by 2 into cos x minus y by 2. Okay, so okay, as cos of minus theta, of course it is cos theta only. So omega t minus phi by 2 you can get here. Then 2a cos of, this is omega t plus omega t, 2 omega t plus phi by 2 into cos of minus phi by 2. So this further we can write y is equals to 2a cos of minus theta, cos theta, so cos phi by 2 into cos of 2 omega t plus phi by 2. If you write here, if you split this denominator, then cos of omega t plus phi by 2 we will get. So this is in the form y is equals to a dash cos of omega t plus phi by 2. So then amplitude a dash, so here what they are asking, intensity. So intensity here, how can we write? A square in terms of a square. As I said, a dash here, so a dash square. So I is equals to a dash square. A dash is what? This whole term will become a dash. So then a dash square means 4 a square cos square phi by 2. That's all. Whereas a dash is equals to 2a cos phi by 2. 4a square cos square phi by 2. This is how we have to obtain. We can show it. So then conditions here, I will write conditions. Constructive interference condition. So for constructive interference, that means bright fringe, when will you get? When that phi by 2, when that phi by 2 is equals to, okay, it's very close to this. Okay. So here I am writing when phi by 2 is equals to n pi, that means when phi is 2n pi, then constructive interference will occur. Okay. Similarly, when that phi by 2 is equals to n pi plus or minus phi by 2, destructive interference will occur. That means phi is equals to 2n pi plus or minus pi. Okay. So these are the conditions for occurring the dark and bright fringes. Let's move on to the next question then. Eighth one, state the postulates of Bohr's atomic model. Okay, very important and easy, of course. So Bohr's atomic model postulates, what are they? Each and every electron will revolving around the core part, what we are calling it as nucleus, in a specific path, what we are calling it as orbits. Okay, and there that stationary orbits we can also call them as shells, energy shells. These energy shells are arranged in an order, I mean they are named as KLMN shells. Okay, and until and unless that electron will come out of that orbit, there won't be any kind of transmission of energy, no gain, no loss. So energy won't be transmitted, or I mean either it won't emit or it won't gain when it is revolving around the electron in its orbital path. No gain, no loss. And next one, the angular momentum of each and every electron which is revolving in that orbit will be quantized. So angular momentum is quantized. So these are the main postulates of the Bohr's theory. Okay, so all that electrons will be revolving around the nucleus in the specific paths, what we are calling them as orbits, and then those orbits, as we are calling them as stationary orbits, or we can say them stationary shell. So their shell energy levels are mentioned as KLMN levels. And then when until and unless that electron will come out of its orbital path, then there won't be any kind of energy transmission. So no gain, no loss when it is inside, I mean when it is traveling along the, I mean revolving along the its orbitalic path. And then angular momentum of each and every electron is quantized. Obtain Bohr's quantization condition for angular momentum of the basis of wave picture of electron. So see here, suppose if we consider that nth orbit, okay, then angular wavelength of it, that electron can be taken as, suppose if this is the nth orbit and let r is the radius of it, in terms of Planck's constant, lambda is equals to h by mv, we can write, which is the momentum of the electron. Okay, and from this one we can say that 2 pi r, perimeter of that orbitalic path, is equals to, as it is nth orbit, 2 pi r is equals to n lambda. Then lambda, if you substitute here, 2 pi r is equals to nh by mv. If you bring mv to this side and 2 pi to this side, mvr is equals to nh by 2 pi. That means L is equals to and times of h by 2 pi. This represents the condition of angular momentum on the basis of wave picture. Okay, so this is how you can solve this question. Next, let's move on to the next question then. Yeah, explain the process of release of energy in a nuclear reactor. Draw a label diagram of a nuclear reactor and write the function of each part. Okay, fine then. First I'll draw that. See, then it consists of a closed shielding in which so here this is nuclear chamber, these are moderator, and there will be control rods here. Okay, and this here heat pump will be connected to here. So this is a heating chamber. Okay. So see here, this is the general prototype of nuclear reactor here. This is shielding, and this is moderator, we can say. This is control rod. This is the heat chamber. So pump arrangement, here also pump arrangement will be there, just for this is for hot water and this is for cold water. Okay, these are the general diagram of, and here this inside that fission process will occur. Okay, so here energy, release of energy in a nuclear reactor. We all know that nuclear reactor will function on the basis of a nuclear fission reaction. Okay, so where there that enriched nuclear material, just like uranium, if it is bombarded with the neutron, then by releasing some amount of energy along with neutrons, some amount of energy will be released there, and again those neutrons whichever are evolved after that reaction, one each, 3 neutrons will be released, right? So one each will be again going to have same kind of reaction how it was happened earlier, and each time that amount of energy will be released out. So here that energy, by the bombarding that nuclear radioactive element, we are releasing the nuclear energy. So that energy, with just by having some arrangement, we are converting it into steam energy. So that steam energy we are driving onto the turbine. So that steam energy is it's very high and powerful one. So that steam energy will be further converted into mechanical energy here. So here heat energy, and here heat energy will be this heat energy, that's what steam here. This will be driving this turbine, so that means we are giving this mechanical energy as input, and further we will get output what? Electrical energy. So energy conversion process you can see here, nuclear energy to heat energy, I mean this is what steam energy, and further it is converted into mechanical energy, and then mechanical energy into electrical energy. Okay, so how this explain the process of release of energy in the nuclear reactor, how it's going to be happen. Now here regarding the function of each part, it's one of the very easy topic from this chapter. See here, nuclear fuel. First you can talk about nuclear fuel. So the nuclear fuel which we are going to use in this reactor is an enriched uranium. Okay, it's a highly radioactive element, and then that will be bombarded with the help of a neutron, and their energy will be released out. So that is very high energy, and that is very fast reaction. So then if the reaction goes on just like that, when there is no controlling on the reaction, then the system entire thing will be it will be just like blasted. Okay, so that means that high enormous amount of energy will be released for an uncontrolled chain reaction. This is chain reaction, right? So then you have to control the chain reaction. That means during that process, that controlling will be happen here majorly with the help of two things. One is by speeding down the neutron. So to slow down the neutron, we are having moderator. Moderator will slows down the neutron. Okay, so that moderator basically are heavy water or deuterium. Graphite rods also we can use. And then as I said, the chain reaction should be controlled. So for controlling the reaction, we are using control rods. That control rods will absorb the number of neutrons by maintaining the sufficient number. It's not like that whatever the number that is going to be released, that every neutron is absorbed by it. Will maintain the sufficient number which are required to sustain the reaction consistently, and the rest will be absorbed by the control rods. And next, coolant. We have to use coolant. Why should we use the coolant? Since as we are converting this nuclear energy into heat energy, so heavy heat will be developed in the chamber. So that system should be cooled every time. Basically coolant is nothing but a cold air or else water we will use. Okay, so coolant is required just to cool down the system, to prevent it from the extra high heat that is developed evolved out while reaction taking place. And then shielding. So what is this shielding here? So this entire reactor can be set down in the frame that's encased within a shield, because as I said, though certain proper arrangements are taken, the best materials are used to prevent the heat out or to prevent the radiation out, but still that less amount of some amount of radiation will come out of it. So to prevent it, to minimize the radiations that are going to be out of the reactor, we are going to put this in a casing which we are calling it as shielding, okay, to prevent from the radiations that are going to be out while the reaction taking place. So this is what about this nuclear reactor as well as the part function of each and every part of this. Okay, fine. In examination you have to explain it very neatly. Right then, next question. I think a diagram is not visible properly, it may be. In this one, in the following diagram, the junction diode forward biased or reverse biased. Okay, draw the circuit diagram of a full wave rectifier and state how it works. Okay, fine. Let's see now. First, the diagram. Here I am redrawing it. This is plus 5 volt. This is grounded. Okay, see, this is a P type diode. This is P side and this is N side. See, P side is basically connected to the lower potential region, N side is connected to the higher potential region. This is the lower potential and this is the higher potential. So what can we say here? P side is connected to lower potential and N side is connected to higher potential. This is reverse biased. So it's a reverse biased here. Okay, draw the circuit diagram of a full wave rectifier and state how it works. All right, so here I am drawing the full wave rectifier. Please see here, it consists of a transformer arrangement. This is the transformer arrangement. We can say this as primary coil, this is the secondary coil, and where a diode, two diodes are there here. Two diodes you can draw here like this, and there is a center tapping where the load is connected across. So let these points are here, X, Y here, and this is the diode D1 and this is let diode D2. Points, let it be A, B. Okay, fine. This is P1 and this is S1. Input side, this is V in. So full wave rectifier, how it's going to work? This is the simple arrangement of a full wave rectifier. It consists of a transformer and this is the primary coil of the transformer and this is the secondary coil of the transformer. To the secondary coil of the transformer, that means output side, two diodes D1 and D2 are connected as shown in the figure like this. All right, now here we are giving AC input. What input we are giving? AC input, which consists of, that's nothing but alternative current, so that the direction of the current will be varying for every half rotation of the coil in the armature coil in the generator. Fine. So for every half revolution or for every half cycle, you can say, for every half cycle direction of the current is reversed. Okay, fine. First we are giving the input here. When you are giving the input, say this is plus and this is minus then. So the P side of the diode D1 is connected to positive terminal, whereas P side of the diode T is connected to negative terminal. So in the first half cycle, D1 will conduct, D2 it won't conduct. Since D1 is conducting nothing but D1 is in forward biasing, D2 is in reverse biasing. So in the forward biasing, D1 will conduct. So then cycle will become A, X, Y, A. So like this the propagation of the current will be during first half cycle. During the next half cycle, D1, so here negative will be there, here positive will be there. So negative input is given to D1, which means the primary side, P side of the PN junction diode is connected to negative terminal. We can say that D1 diode is said to be in reverse biasing. So D1 is not functioning here in second half cycle, D2 will function. So then this will be positive, right? The direction will be like this. That means B, X, Y, B. So in both cases, whether it is for positive half cycle or for negative half cycle of the given input AC, the rectifier is going to function. So there is no interruption here. unlike how it is happening in half wave rectifier. It will conduct only during one positive half cycle, whatever, one half cycle. So it won't work in the another half cycle. So you won't get a full wave output. But here it is not like that. In full wave rectifier, whether it is a positive half cycle or negative half cycle, during both half cycles, the diodes will be operating. But here, D1, D2, if I take two rectifier, two diode, two PN junction diodes here, one diode will operate in one half cycle, then by that time another will be not operating. That means the one which is operating, that will be in forward biasing, the one which is not conducting, that will be in reverse biasing. So however the process it goes on, the full AC input will be converted into, the full waveform will be converted and obtained. That's what we are calling it as full wave rectifier. So here, during first half cycle here, D1 will conduct. During next half cycle here, D2 will conduct. And finally, we will get like this. So rectifiers will convert that AC to DC basically. They will convert alternating current to direct current. So then you can see here some presence of these what I can say, this kind of waveforms here. Actually it won't give the pure DC. It consists of some ripples. That AC full wave rectifier, whatever you may take, whichever is converting from AC to DC, by just conversion it won't give that pure DC. It consists of some ripples. Those ripples can be eliminated with the help of by placing some filters. So filters can be placed and we will get finally some pulsating DC. Okay. So this is what the process of the full wave rectifier. Okay. Very simple and very easy. See the next question here. 11th question. In the following diagram, which bulb out of B1 and B2 will glow and why? So see here, I think a diagram is visible here. Fine. There is the diode D2 here and diode D1 here. Yeah. B1, B2 bulbs are there. So here, this is P side, this is N side. P side here it is connected to positive. And here if you see, this is P side, this is N side. P side of second diode is connected to negative. So this is reverse bias. If it is reverse bias, open circuit, bulb B2 won't glow. This is forward bias. So then B1 will be glowing. So bulb B1 will glow in this one. B1 will be glowing. Since D1 is forward bias, D2 is reverse bias. Draw a diagram of an illuminated PN junction diode of a solar cell. So this is the PN junction diode and solar cell illuminated. You can mention like this. This is the diagram here. Okay. So that it will convert that solar energy into useful electrical energy. Explain briefly the three processes due to which generation of EMF takes place in a solar cell. So here process number 1. Here when the energy of the incident solar light, so that means solar energy, whatever, incident energy, if it is greater than the energy gap in the semiconductor diode, that is PN junction diode, then electron hole pairs will be formed. First one, in the first process, electron hole pairs will be formed when the energy that's going to incident is greater than the energy gap of the semiconductor. Second, these electrons and holes will be separated. Electrons and holes will be separated due to what? Due to the electric field existed in the depletion region. Okay. Third, these electrons which are moved, mostly they will move to the frontward, which are in contact with the front side, that will be adjusted towards N type. Electrons will be to N type. Similarly, holes that are in contact with the back end will be moved towards that another whole region which we are calling as P region, P type. So as a result, what will be obtained? Photovoltaic effect will be occurring, so that EMF will be generated. So in the first process, when the incident energy is greater than the energy gap of the semiconductor, then electron hole pairs will be obtained. those electrons and holes will be separated due to the electric field that's present in the depletion region, and then those electrons will be moved towards the n side, holes will be moved towards the p side. As a result, EMF will be generated. That's what the question asked, right? Three processes due to which generation of EMF takes place in a solar cell. So same solar cell, how it's going to be worked. The solar energy that's going to incident over here will be converted into useful electrical energy with the help of this process. All right, let's move to the next question then. The last one, case study. So till the 11th question we have completed for 30 marks. Section A, 3 questions, 3 2s are 6. Section B, 8 questions, 8 3s are 24. Section C, one case study. That case study consists of 5 marks, 5 questions. So 30 plus 5, 35. An optical fiber is a thin tube of transparent material that allows light to pass through without being refracted into the air or another external medium. It takes use of total internal reflection. These fibers are fabricated in such a way that light reflected at one side of the inner surface strikes the other at an angle larger than the critical angle. Even if fiber is bent, light can easily travel along the length. So see, optical fiber will work on the principle of total internal reflection. First, we should know what is total internal reflection and when it is occurred. The phenomena of reflection of light totally into the same medium when it is traveling from denser to rarer. Okay, then only that will be possible. That phenomena of reflection of total light into the same medium, we are calling it as total internal reflection. So when the light is traveling from denser medium to rarer medium, denser medium to rarer medium, so what will happen generally? It will bend away from normal. So if you are increasing at one certain angle, one particular angle, the light ray will be grazes out along the surface. In such case, angle of refraction will become 90 degree. At what angle of incidence that light ray will graze out along the surface, we are calling it as critical angle. Let it be IC, or let it be C here. IC is equals to C. Now if you increase the angle of incidence greater than the critical angle, if I is greater than the C, then the light will be reflected totally. This which we are calling it as total internal reflection, where you can write expression for the refractive index in terms of critical angle is mu is equals to 1 by sin C. Now here, so this is the incident light ray that incident on the optical fiber, which will be undergone for, which will be suffering for multiple reflections totally internally, just like that. So this we are calling it as core, and then cladding will be there here like this, cladding. Okay, so this is light ray. This is the diagram over here. Okay, just a minute. I think, yeah. So see here, this is how it will be. What happened? So whoever are watching, am I visible and audible? I got stuck here.